This is Chemistry Unit 6, Chemical Composition, the mole. Another way to measure the amount of a substance is to count the number of particles of that substance. When talking about the number of atoms, the number of individual atoms in a sample is ridiculously large. So counting the individual atoms is not practical. So just as a dozen represents 12, that's conversion factor, right? We can now say that 1 mole, M-O-L-E, represents 6.02 times 10 to the 23rd particles of a substance. So here's what the conversion factor looks like. You see 1 mole, or you can also write 1 MOL. You can cut off the E for a slight shortcut, equals 6.02 times 10 to the 23rd particles, or atoms, or molecules. Now this number, often referred to as Avogadro's number, is named in honor of the Italian scientist Amedeo Avogadro Quarenga, on whose work the concept is based. And here's an image of him. So what exactly is a mole? Well, 1 mole is a lot of things. And to help you understand the magnitude of this number, just how big it really is, I think these comparisons will help. So if you had 1 mole, or 6.02 times 10 to the 23rd marshmallows, that would cover the United States 600 miles high. So that's a lot. If you had a mole of hockey pucks, that would be equal to the mass of the moon. But maybe this money reference will be the best way to help you understand this. If 1 mole of pennies now, not even dollars, were divided up among the Earth's population, each person would receive 1.5 times 10 to the 14th pennies. If you spend $1 million a day, you would use up your wealth in 4,000 years. Now this seems awesome, right? Like that's, a lot of pennies, it's a lot of money, but life would not be comfortable though, because the Earth would be buried in copper coins 420 meters deep. So I hope this helps you understand the mole is a large, large number. So that's 6.02 times 10 to the 23rd is a lot. Now there is a Mole Day Society because this is an essential component of chemistry. So there's a whole society based on this. There's an actual Mole Day. It's October 23rd. Get it? 10 to the 23. Okay. So here's the website. I will post that if you are curious. But this is another great video to watch. It's a TED Ed video about how big a mole is. So I will post that as well if you are interested. Now, how can we use Avogadro's number in a calculation? Well, look at this first example. Look at the question. It says how many moles of magnesium, magnesium's an element, right, make up 1.25 times 10 to the 23rd atoms of magnesium. So if you know how many atoms of magnesium you have, how many moles is that? Well, just by looking at that number, right, 1 mole is 6.02 times 10 to the 23rd atoms, right? Now here you have 1.25, so that's less than 6.02, so your answer here should be less than 1 mole. But let's prove it now. So this is why we learned dimensional analysis or factor labeling. It's to solve problems that look like this using another type of conversion factor, which will be the mole. So you start with the number that was provided, 1.25 times 10 to the 23rd atoms of magnesium. That's my starting point. Now you set up your t-square, and if you're trying to answer how many moles there are, that means atoms needs to go away and you need to be left with mole. So here's our conversion factor, right? So 1 mole equals 6.02 times 10 to the 23rd atoms. Why did I put 6.02 times 10 to the 23 atoms on the bottom? Because I want the atoms to cancel. So 1 mole is on top, atoms is on the bottom of this t-square. Now to solve this, remember when you are using scientific notation, which is this times 10 to the 23, you don't type in times 10. You'll hit 1.25, the EE key, to the 23rd. Now I also recommend using parentheses. Some of these problems will be getting a little bit longer, and it just helps the calculator understand what you're trying to type in. So parentheses is not mandatory. It's just a suggestion on my part if you want to make sure that your problems will be set up as you want them in the calculator. But in any case, go ahead and type this in. So it's 1.25, the EE key to the 23rd. You can times it by 1 if you'd like to, but that's not necessary because it'll still be itself. And then you divide by 6.02, the EE key to the 23rd. And then your answer with correct significant figures, you want 3 significant figures because that's what you started with, is 0.208 moles of magnesium. So this is if you are provided with atoms and you're trying to get to moles. Now remember that this was less than 6.02, right? So your answer should have been less than 1 mole, and it actually is. All right, one more example. So the question is, how many atoms of sulfur are present in 0.75 moles of sulfur? So now you have 0.75 moles of sulfur. How many atoms is that? So we can use the same conversion factor. And again, we can kind of predict our answer here. 0.75 is less than 1 mole. So our answer should be less than 6.02 times 10 to the 23rd atoms. But let's prove it. So again, we're going to start with what was provided in the problem, which was 0.75 moles of sulfur. And here's our conversion factor. 1 mole is 6.02 times 10 to the 23rd atoms. Now, why was 1 mole put on the bottom of the t-square? Because I'm trying to eliminate moles and solve for atoms. So the 6.02 times 10 to the 23rd atoms will be on the top. Now, to solve this in the calculator, you will multiply across, right? Because the numbers are next to each other. So you'll take 0.75 and multiply it by 6.02, hit the EE key to the 23rd, and then make sure you round your answer to have 2 significant figures because that's what was in the problem. So my answer is 4.5 times 10 to the 23rd atoms of sulfur. And you can see that this is slightly less than the 6.02 because I don't have 1 mole. 0.75 is less than 1 mole.